Transformers are like those party guests who can't stop chatting about everything under the sun. Text, audio, images, you name it. They create art and whip up coherent narratives from nothing but a few prompts. Talk about multitasking. The original Transformer, created by Google back in 2017, was intended for text translation. Think of it as the translator who first ventured into the world of language. Suddenly, it opened up a Pandora's box of natural language processing applications. And who knew a simple model could cause such a ruckus in the tech world? When generating text, these transformers play a little game of what's the next word, based on what came before. It's an iterative dance that leads to longer and more coherent narratives. Imagine a writer who's had one too many cups of coffee, just typing away. Now let's talk about those attention blocks. They're like the smart glasses of machine learning. These wonderful gadgets update word meanings based on their context, reminding us that words can mean different things depending on the context. It's like saying you're the apple of my eye in a fruit salad versus a romantic dinner. Training these models is kind of like prepping for a big exam. You need a solid overview of what's going to happen, from the beginning to the end of the network. It's rigorous, kind of like trying to remember every single detail of a 10-season TV show before a pop quiz. Machine learning models have a knack for recognizing patterns, which is like spotting your ex at a bar, awkward but necessary. Rather than relying on explicitly programmed instructions, they learn from data patterns, making them versatile in tasks like text predictions. Who knew algorithms could be social? Deep learning models, like the celebrity in the tech world, GPT-3, flaunt billions of parameters, making them the hotshots of machine learning. This complexity is what enables them to learn intricate patterns effectively. Think of them as the detectives of the data world. The input data for these savvy models is formatted as arrays of real numbers, like a fancy salad of numerical goodness, which can be one-dimensional or multidimensional. This structure is crucial as they swim through multiple layers of deep learning. Talk about going deep. Model parameters, or weights as we call them in the deep learning club, play a crucial role in processing our data. Think of them as those friends who help you carry your groceries. Without them, the shopping trip would be a total disaster. Word embeddings are like the MapQuest of the language world, defining words as vectors in a high-dimensional space. They help us grasp meanings through geometric relationships, so yes, math can actually be useful beyond high school. The video hilariously demonstrates how semantic relationships can be unearthed by playing around with vector differences, kind of like trying to find the female equivalent of a male name by moving vectors. We've come a long way from just pointing at stuff in the real world. Examining associations between countries and historical figures using vector arithmetic shows how these models can juggle complex cultural and historical relationships. It's like figuring out who's dating whom in a soap opera, complicated but entertaining. Calculating the dot product is a fancy way of saying we multiply corresponding components and sum them up. Essentially, it's like a very mathy way of measuring how well vectors get along at a social gathering. Word embeddings do more than just represent individual words. They're also like that friend who remembers all the juicy context. This extra understanding allows the model to grasp the relationships between words, making predictions richer and more flavorful, like a well-seasoned dish. However, models like GPT-3 have a context size limitation, which means there's only so much info they can handle at once. This limitation can affect the smoothness of conversations, leading to those awkward moments where one person is talking about pizza while the other is in deep about quantum physics. The unembedding matrix, known as WU, is like the ultimate translator, taking the final vector and morphing it into a probability distribution for word prediction. It's learned during training because let's face it, nobody just stumbles into a job without prior experience, right? Let's not forget about the softmax function. It takes a random list of numbers and transforms it into a valid probability distribution, kind of like making sure nobody leaves a party sober. Every value sums to 1, ensuring we have reliable predictions. And did you know that adjusting the temperature parameter in the softmax function can spice up our word predictions? A higher temperature brings in more creative outputs, while a lower temperature plays it safe, meaning less risk of an embarrassing word salad. The whole process of inputting text into AI and utilizing matrix multiplication is essential for those fun word predictions. It's like inputting your chaotic thoughts and getting organized sentences in return. Honestly, who wouldn't want that in their life? Foundational concepts like softmax and matrix multiplication are the bread and butter of word prediction in AI. They serve as the building blocks for modern advancements, proving that even the most complex systems have humble beginnings, just like us at brunch.